Okay, so let's start. So today we are having a very invigorating session on Wi-Fi, and to present about Wi-Fi and the new standards that are emerging, we have Ankit Sethi with us. Ankit is a senior design engineer in NXP and has been with us for over a decade now. So welcome, Ankit, and let's start the presentation now.
Okay, yeah. Thank you, Akhil. Thank you for this nice introduction. I hope my audio and my visual both are on and everyone can see it together with the presentation also.
Yes.
Okay, yeah.
Your
Thank you,
video is
Akhil.
turned off, sir.
Video is off. Uh,
No, video is on. You can turn off the video.
oh, I should.
Yeah, that's fine. It's up to you. If you want to turn it on, you can keep it on.
Okay, yeah. Let's have the video on. It will have in better interaction. Yeah. Okay, so welcome everyone, and it is my pleasure to present in this NXP Campus Connect and to meet all the talented and motivated engineers as well as the upcoming engineers and the community of students that we have with us. And just to give a brief overview of what we would be discussing today. So we would be discussing on the evolution of 5 technology of Wi-Fi and specifically spending some time on Wi-Fi 6. So Wi-Fi, as we all know, has been one of the dominant technologies to access internet. We find Wi-Fi present everywhere today in every kind of device, say laptop, mobile phones, smart devices, IoT devices, watches, smartwatches, you name and you will find Wi-Fi technology. The number of devices that want to get connected to Wi-Fi is ever increasing. And this technology has become a dominant technology to access internet. Further, the demand for throughput on Wi-Fi has also been increasing. The number of devices that want to get connected is increasing. The kind of topologies that we want to support has been numerous now in Wi-Fi. And to support all of it, the Wi-Fi standard has been evolving. So Wi-Fi standard has been very proactive in adhering to and in understanding the needs of the customer and the market and how it has evolved over time that we will see in this presentation. So specifically, there is a group in IEEE, which is an 802.11 and IEEE standards working group that actually looks into how the Wi-Fi technology should evolve, what modifications needs to be made, what new additions needs to be made to the Wi-Fi, and they look across all layers of Wi-Fi, be it the link layer, be it the MAC layer, be it the file layer. There is a group that looks into the security aspect of Wi-Fi also in IEEE. So what we would be focusing today is the evolution of Wi-Fi technology from the physical layer perspective. And that is what would be the focus of this discussion and presentation. And specifically, we would be spending more time on Wi-Fi 6, which is one of the recent standards of Wi-Fi that the market has adopted. On standard fronts, we have moved a bit forward, but currently the market has been adopting Wi-Fi 6, and we will see the benefits of Wi-Fi 6 from the 5 perspective. Okay. So just to mention, so NXP has been one of the dominant players in the Wi-Fi market, and it has a rich portfolio of Wi-Fi chips that it offers to top tier customers in automotive market. It caters to also industrial IoT, mobile market, as well as communication infrastructure market. So NXP has been one of the dominant player here, and it is a well reputed and a well respected community in the market for its offerings of Wi-Fi product. And let us now deep dive into the session now on the more technical fronts. So let us first set the agenda on how we will be proceeding about this presentation. So firstly, we will be going over a brief overview of the evolution of Wi-Fi technology up to Wi-Fi 6, how it has evolved, what are the different things that have come into picture on Wi-Fi specifically from 5 perspective. And then we will deep dive into Wi-Fi 6.5 features, which would include 4x tone nomenclature, OFDMA, which is a new technology that got introduced into Wi-Fi 6, the 1024 QAM MCS that got introduced, as well as the downlink and uplink OFDMA and MU transactions that got introduced into Wi-Fi 6, and how all this help in supporting higher throughput requirements, dense environment connectivity, etc. and etc. So that would be the way we would be going over the topics here. Okay, so now let us first try to understand the evolution of Wi-Fi over timeline, how it has evolved. So the first standard of Wi-Fi, which is 802.11b, it got formalized in 1999, and this was a CCK based standard with the data rate of up to 1 to 2 Mbps. And then slowly we went to OFDM kind of a standard, which is 802.11g, that got formalized in 2007. So we see there is a big, there is that tenure to from it for it to evolve from 802.11b to 802.11g is around 8 to 9 years. So at this time, Wi-Fi was just picking up, and the OFDM based Wi-Fi first got introduced in 2007. So it is also called 802.11g. Both are called Wi-Fi as of now, which operate in 2.4 gigahertz band. And the bandwidth that can be allocated to a user is 20 megahertz. We should understand that in 2.4 gigahertz band, the available band that is available, that is present is around 100 megahertz. So at most we can accommodate say 5 users in a 2.4 gigahertz band. However, as soon as this technology of OFDM got introduced for 802.11g Wi-Fi, there was a significant traction of Wi-Fi in the market and more throughput requirement, more connectivity requirement. The demand came from the market. For the same, we there was another technology that got evolved from Wi-Fi to Wi-Fi 4, the fourth generation Wi-Fi, which got formalized in 2009. And what it did was it expanded the bandwidth from 20 megahertz to 40 megahertz that could be allocated per user, as well as it extended itself to 5 gigahertz band also. And the reason it extended to 5 gigahertz band is, as we mentioned, in 2.4 gigahertz band, only 100 megahertz bandwidth was available. So 5 users could be, say, in a particular space, 5 users could at most be transacting together. But now in 5 gigahertz band, we have an entire 1 gigahertz band available for Wi-Fi transaction. Hence, it supports a large number of users in a particular space that could transact together. Further, after this, there was again the demand for throughput, the demand for connectivity kept on increasing. It is increasing today also. And the Wi-Fi fourth generation had to evolve into Wi-Fi fifth generation technology, where the bandwidth was increased from 40 megahertz to 160 megahertz, specifically catering to very high throughput kind of applications. This was specific to 5 gigahertz only. 160 megahertz is not present in 2.4 gigahertz. Hence, this specific technology is present for 5 gigahertz band only. However, as we know, the throughput demand, it keeps on increasing, and the number of devices, specifically after this, when we had mobile coming in, the number of devices that wanted to get connected, all the smart devices coming in that want to get connected to Wi-Fi was increasing tremendously. And we required some specific and some huge modifications in Wi-Fi technology that could support multiple users together. And by multiple, I mean many users together. This technology that got evolved was Wi-Fi 6, which is more or less it's more or less got formalized in 2020 and is currently one of the recent technologies in the market that people and that customers are accepting now. It is present not only in 2.4 gigahertz or 5 gigahertz band, however, even in 6 gigahertz band. So there is a variation of Wi-Fi 6, which is called Wi-Fi 6E, which means Wi-Fi 6 extended. And what it means is even the 6 gigahertz band can be used now for Wi-Fi. This band also gives us an entire 1 gigahertz of bandwidth available for Wi-Fi. There have been numerous enhancements that have been proposed in Wi-Fi 6. The 5 enhancements we will be going over, some special 5 enhancements we will be going over. The bandwidth that is available is 160 megahertz per user, in this case, the maximum bandwidth. And just to give a prelude, what is also is getting discussed in the standard is another technology, which is 802.11be, which plans to get formalized in 2023, which is the seventh generation of Wi-Fi. The IEEE standards team for Wi-Fi is currently working on it. More or less, most of the work is done. We expect that the technology more or less will be formalized here. Again, yeah, it caters to the demands of the market, which requires like AR, VR kind of applications, how we can have multi-link transmissions, etc., etc. So this is the current technology of Wi-Fi that is getting discussed in the standards. However, the technology that is currently getting adopted in the market is 802.11ax, which is a Wi-Fi 6 or 6E, and that we will be now deep diving into. Okay, so firstly, before moving to Wi-Fi 6, let us see how the technology evolved from up to Wi-Fi 6. So as we discussed that 802.11g, which is also called legacy, then we have 802.11n, which is called HT, which is the second one. And the third one is 802.11ac, which is also called VHT. So how this technology evolved over time, let us see. So the bandwidth that was present per user was 20 megahertz for legacy. It continued to be 20 megahertz for HT also. However, the number of tones that got packed in 20 megahertz, so this is an OFDM technology, so the number of tones that got packed in 20 megahertz for HT increased to 52. And by +4, we have the pilot tones. The pilot tones are required by the pilot tones are included in OFDM symbol construction for better reception at the receiver, so that the receiver can do some kind of better processing and the packet can be received properly. However, the number of data tones, which was 48, it increased to 52, and more data tones got packed in the HT frame format in 20 megahertz band itself. So this improved the spectral efficiency of the technology. Further, it also introduced a 40 megahertz bandwidth that could be allocated per user. Hence, what in that we have 108 data tones that could be sent in an OFDM symbol. It improved the peak throughput of the system and of the transaction. Then this technology got evolved into 802.11ac, which is VHT. The spectral efficiency remained more or less the same. So for 20 and 40, we have the same number of data tones, 52 and 108. However, for 80 megahertz and 160 megahertz, we have now the more number of data tones that could get transmitted. So per user, we can have the allocation of bandwidth of 80 megahertz and 160 megahertz to further improve the throughput of the transaction. On frequency band front, the 802.11g technology catered to 2.4 gigahertz. The .A technology catered to 5 gigahertz. HT technology caters to both 2.4 and 5 gigahertz, and VHT, because of the increase in the bandwidth, is catering only to 5 gigahertz band. On the MCS, the modulation scheme, the modulation and coding scheme that is used. So on each data on an OFDM symbol, we send a particular constellation symbol. So a particular constellation symbol, what we do is we have multiple bits that construct one constellation symbol. So for 64 QAM, we have say 6 bits that constructs one particular constellation symbol. So we could transact say 6 bits on a particular data tone in an OFDM symbol in case of legacy. So that is a 64 QAM, and we used a 3x4 encoder rate here. As the technology progressed and on the analog and the RF front end, we had better devices coming in. What we found is we could use higher constellation also for the transactions. So in 802.11ac, what we see is we start using 256 QAM, which is a more denser constellation with 5x6 coding rate. What we will now see in Wi-Fi 6, we will use a higher constellation because the RF and the analog technology has progressed and has matured enough so that it can send a denser constellation. On maximum data rate that we have, say for legacy, the data rate was per user data rate was limited to max throughput was 54 Mbps. So this is the 5 data rate that I'm talking about. And we had a 10-fold increase in the data rate, more than 10-fold increase, I would say, in the data rate when we start using HT, which is 600 Mbps. The main reason for this increase comes from, say, because of we have maximum more number of streams coming in and higher bandwidth of use that we have. Again, when we move to VHT, the number of streams that we have increases to 8, and the data rate that we have is 6.8 Gbps, which is more than 10 times the 10 times the throughput that we had for HT. the increase in the data rate here comes because of the higher bandwidth allocation that we can have to a particular user, the higher constellation, as well as the more number of streams that we can spatially multiplex in a particular band. On the OFDM symbol, we are aware that we require to put a guard interval. This guard interval is required to avoid any kind of intersymbol interference. And the guard interval support was first for 0.8 microseconds only for legacy frame format, for legacy technology. Then there was a requirement and a discussion to have a shorter guard interval for HT. Now, just to understand, give a brief understanding on the guard interval. So what happens is the longer the guard interval we have as compared to the OFDM symbol duration, the proportion of the guard interval, if it is longer, then the efficiency of the OFDM symbol decreases, the throughput decreases. However, we need to have a guard interval to avoid any kind of intersymbol interference. In scenarios where say we feel that the channel delay spread is limited and it is not high, we can consider shorter guard intervals. So say for line of sight channels or where the delay spread of the channel is low, the HT technology introduced a shorter guard interval and thus in turn allowing to improve the efficiency of the OFDM symbol transaction. And this got extended to VHT also. On the encoder front, the legacy technology used only BCC encoder. However, as the technology evolved and as the implementation and the designs became, so LDPC technology is a complex technology, but as the design evolved and as the industry matured towards complex designs, LDPC technology, encoding technology also got introduced in HT. So LDPC encoding technology, the benefit is it gives a better rate at a lower SNR regime, and hence helps in improving the system efficiency and the throughput that a user observes in say mid-range or low-range SNR regimes. Similarly, this LDPC technology got extended to VHT also. So we already discussed that max number of SU streams got increased. The number of streams that we can spatially multiplex for a particular user got increased from 1 to 4 to 8. And a new technology that got introduced for VHT is multi-user. So what it means is we can spatially multiplex up to 4 users now. So an AP or an access point can now communicate with 4 users, say in downlink specifically in VHT. The number of streams that it could send to a particular user is 4. And the total number of streams that an AP and access point can send is 8. So this helps in connecting with multiple users, specifically in downlink by spatially multiplexing them by the access point. Okay. So now we move to Wi-Fi 6 and try to understand the benefits of Wi-Fi 6. Again, what we need to cater to, what we need to understand is market has always been demanding higher throughput, more devices that needs to get connected to an access point. And how Wi-Fi 6 technology enables it, we will see that. So firstly, it is through better spectral efficiency. It delivers on peak throughput improvement, and it is better suited to dense environment where we have multiple devices getting connected. Some devices may have low throughput requirement, some devices may have high throughput requirement, some devices may have better want a very good latency, and how Wi-Fi 6 technology helps in improving the latency management also. One more feature that got introduced in Wi-Fi 6 is a longer range that got introduced in Wi-Fi 6. So it can cater to a longer range now as compared to the previous Wi-Fi 5 or Wi-Fi 4 technology. So a new packet format got introduced in Wi-Fi 6 to so as to be able to have a longer range transactions for to meet better customer requirements at that period of time. So these are the 5 feature highlights that we will be going over. And the SU and the MU throughput increased is through, say, the 4x tone spacing, which we will be going over. So the tone spacing of OFDM tones is reduced to 1/4 here. We have a guard interval of 0.8, 1.6, and 3.2 microsecond support. The throughput increase is also because now we have support for 1024 QAM. We will be going over this also. And the total number of streams that we support, the spatially multiplexing possible is 8 streams. In MUMIMO, when we have multiple users who are getting spatially multiplexed, the support for 11AX has been now introduced to 8 users now. So this further improves the efficiency in dense environment when multiple users are getting connected. One of the major new technology that got introduced in Wi-Fi 6 is OFDMA. And what we will find is how we divide the bandwidth, available bandwidth between different users, and how it helps in improving the overall system throughput and better latency management. Together with this, what we also have is an uplink MUMIMO or OFDMA that got introduced in Wi-Fi 6. So the uplink was not downlink. MUMIMO was present in 11AC. However, uplink MUMIMO was not present in 11AC, which got introduced in Wi-Fi 6. And both of these now help in managing dense environment better, where many devices are getting connected to an access point. And on the extended range front, as we discussed, that there is a new packet format getting introduced to for having transaction getting on a longer range in Wi-Fi. And some of the features that we will see for this extended range transaction is preamble boosting, the DCM, which is dual coded modulation, and longer GS. So we will be briefly going over all of these also. Okay, so first let us go over the 4x tones nomenclature that got introduced in Wi-Fi 6. So what is 4x tone? What does it mean? So in frequency domain, if we were to compare, say for L, HT, VHT, the delta F between the tones, so OFDM tones, the distance in the frequency domain was 312.5 kilohertz. And in time domain, if we were to see, an OFDM symbol was 3.2 microsecond together with a GI. And GI could have been 0.4 or zero point 0.8 microsecond. Now, when we move from here to U, which is Wi-Fi 6 technology, what we see is the delta F has got reduced. The tone spacing has got reduced from 312.5 kilohertz to 78.125 kilohertz, which is 1/4 of what it was here. So now in 20 megahertz band, we are packing more number of tones. However, what we also should understand is in time domain, we are increasing the symbol duration from 3.2 microsecond to 12.8 microseconds with a guard interval options of zero point 0.8, 1.6 or 3.2 microseconds. In hue, what has now happened is we are now packing more number of tones in the 20 megahertz, say for example in a 20 megahertz band. However, we are also increasing the symbol duration by 4 times here. Though we should understand that the guard interval duration is not increasing by 4 times, we have an option of guard interval of 0 0.8, 1.6 or 3.2 microsecond. So this will further improve the efficiency of the OFDM symbol transactions. So if we were to understand, say in case of HT-VHT, we were having 56 tones. In general, if say the number of tones were to increase by 4, it should have been around say 56 into 4, which should have been around 224. However, the number of tones that we have in hue here is now 242. And this is because we have an optimized guard. So between the two bands, we have a guard band. Say between 220 megahertz band, we have a guard band. So some tones are now being optimized and used from those guard bands, and hence it has improved the overall spectral efficiency. So what we see here is for HT-VHT, we had 56 tones out of 64 available tones that we were using. So the spectral efficiency was 87.5%. However, for hue, the spectral efficiency is now 94.5% because we are using 242 tones out of 256 available tones in 20 megahertz. And say similarly in 40 megahertz, we have 484 available tones. For 80 megahertz, we have 996 available tones. And for 160 megahertz, we have 1992 available tones. Increasing the number of available tones has one more advantage. And what we will understand is it is better suited to OFDMA, where we need to finally say slice the available bandwidth to different users. So that is possible if we have more number of tones available. And we will briefly be reviewing this also when we introduce the OFDMA technology in Wi-Fi 6. Okay, so the main benefit, what we need to understand is better spectral efficiency here of U packet OFDM packet format because of the number of tones that we are using, and the guard interval has not been increased by 4 times. We have a support of 0.8, 1.6 as well as 3.2 microsecond for guard interval. Okay, the other technology that got introduced for 1K was the 1K QAM, which is the modulation coding scheme that got introduced for Wi-Fi 6. And this was not present in the previous generation Wi-Fi technology because the RF and the analog technology was not mature enough to be able to send dense constellations. So now we can send 10 bits per constellation symbol on a particular data tone. And this is called 1024 QAM. Two new MCSs got introduced to support this, which is RAID 3x4 coding MCS10 and RAID 5x6 encoding, which is MCS11. So if we were to compare with 256 QAM, what we understand is because we are now sending 10 bits per constellation symbol instead of 8 bits per constellation symbol, the peak throughput now improves by 25%. So previously, an AP could have transacted, say in Wi-Fi 4 technology, an AP can transacted at most using 256 QAM. But now using Wi-Fi 5 technology, it can transact using 1024 QAM. And the peak throughput increase if say the AP transacts using 1024 QAM with its stations can increase by up to 25%. Let us now see how the peak PHY throughput comparison looks like when we compare Wi-Fi 5 and Wi-Fi 6. So say we have a Wi-Fi 5 peak throughput comparison, say for guard interval of 0.4. So let us consider the best case for Wi-Fi 5, where the guard interval of OFDM symbol is only limited to zero point 0.4 microseconds. So what we see is for one stream, it is 0.87 Gbps, for 4 stream 3.5 Gbps, for 8 stream 6.9 Gbps. However, as we move to Wi-Fi 6, for fair comparison, because Wi-Fi 6 has 4 times the symbol duration, the OFDM symbol duration is 4 times. Let us just take for now the 4 times. We increase the guard interval also by 4 times and we keep it 1.6 microseconds. What we see is the peak throughput improves to 1.13 Gbps as compared to 8.87 Gbps. Now this is more than 25%. And the reason for it is one improvement comes from using a higher constellation, a denser constellation of 1024 QAM, and the other improvement comes from the better spectral efficiency because we have more number of tones getting packed in as we saw in the previous slide. So that gives a further improvement, and hence the total improvement is around 29 to 30% in the peak throughput with Wi-Fi 6 technology. So for 4 stream, it is 4.5 Gbps, and for 8 stream, it is 9.1 Gbps. On top of it, what we also mentioned is we can have a guard interval of 0.8 microsecond. That flexibility is given by the standard in Wi-Fi 6 technology. So if we were to use a guard interval of 0.8 microsecond, and because the OFDM symbol duration has increased by 4 times, however, the guard interval has only increased by 2 times here, we see another improvement in peak throughput, 5 peak throughput, which is up to 1.2 Gbps here, 4.8 Gbps for 4 streams, and 9.6 Gbps for 8 streams. And this improvement is up to around, if we were to compare with Wi-Fi 5 technology, the kind of improvement now we see is more than 35% here, up to 38% in the overall peak throughput. The main reasons, just to review, are the improved, the higher constellation that we are using, better spectral efficiency, and the guard interval options that it has provided us. So this is the way the standard has evolved, and it has been catering to higher peak throughput requirements that the market is demanding to for in Wi-Fi 6. Again, the second thing that the market has been demanding is the number of devices that wants to get connected to AP has been increasing. So at our home also we have say multiple, we have say each person has a phone, all of us want to connect our phone to access point. In family, we have multiple members who want to connect our phone to the access point. There are laptops that need to get connected to access point. There are smart devices that need to get connected to access point. To handle such kind of a demand from the market, OFDMA technology got introduced in Wi-Fi 6. And what it does is it divides the frequency band into multiple slices of frequencies that can be shared among multiple users or stations. So in dense environment, previously, say if one wanted to connect to an access point, there was a time sharing that was needed to connect to an access point between the devices. However, here what has happened is the devices can get connected to a particular access point by doing frequency sharing, frequency band sharing. And it is also possible for the access point to give bandwidth to different devices as per the requirement. So say some devices want a higher bandwidth and some devices have a lower throughput requirement, some devices have a higher throughput requirement. So depending on the quality of the service that a device wants, that a station wants, an access point can allocate different kinds of bandwidths and share the frequency among different stations and transact with all the stations together. So this helps in improving the overall system efficiency as well as network efficiency of the system. The possible ways that that an access point can allocate bandwidth to different users is it can allocate 26 tones, 52 tones, 106, 242 tones is 20 megahertz band, 40 megahertz band, 80 megahertz band, or 160 megahertz band. So lowest possible bandwidth that it can allocate to a stay is around 2 megahertz. Depending on the stay requirement, if it requires a higher throughput, it can be 4 megahertz and uh, and etc etc. So yeah, if there is a user which has a very low requirement of bandwidth, what an access point can do is from the band that it has accessed into, it can allocate say only 2 megahertz of band to that user. We will go into more details about this, how this is done in the next slide. And what is done is a single packet is transaction can take place between the access point and the station, multiple stations that can be addressed to multiple users together. So this also helps in improving on the latency requirement. Now each user is connected all throughout the duration. There is no time sharing involved, and hence the latency that the user experience when it is connected on OFDM, it is connected through OFDMA technology is very low because it continues to be connected throughout the duration. There is no time sharing here. And this OFDMA technology is supported both for uplink as well as downlink transaction. By downlink transaction, I mean when AP is sending data to multiple stations, and by uplink transaction would be when all the stations are sending data to AP. So for both cases, this OFDMA technology is supported, and what it means is even say if multiple users want to send data to an AP, then also we have an OFDMA, an AP can allocate different bands, slice the available band into different bandwidths, smaller or larger bandwidths to particular stations so that they can transfer their data as per their requirement, as per their throughput requirement to the access point. Let us see how this is done with OFDMA technology. So this is resource RU means resource allocation. So say for 20 megahertz, we have 242 data tones available, and that is divided say into 26 tone RUs, 26 tone resources. So we can have a 26 tone band allocated to a user here, or another user can be allocated here, or 26 tone can be allocated to a third user, and so on. So what we see is we have say 26 tone resource allocations to to a user, that to different users that we can allocate to. What we also need to see is there is a guard interval here. So say an AP is transacting on a particular 20 megahertz band, then there could be another AP transacting on some other 20 megahertz band here. What we need to ensure is the first AP signal is not leaking into second AP's transaction. And hence we have a guard interval, which is present, a guard band, which is present here to support such kind of, to avoid such kind of leakage into the other user's transaction or the other BSS, that is what we say. Further, what we also see is there are some null subcarriers that get introduced, and this is so that when an AP is transacting with one user, say in a particular 26 tone RU, then the other user has some kind of a tolerance to it, and hence there is no leakage of signal from one user to the other user. Some null carriers, so this null subcarriers have been introduced in this kind of an OFDM frequency domain allocation. So this is for 26 tone RU allocation. Similarly, we have a 52 tone RU allocation that is possible. So we have 452 tone RUs that can be allocated to different users in a 20 megahertz band. So four users say who have 4 megahertz throughput requirement can get connected together with an access point here. So an access point will allocate a 52 tone RU to each of the four users, and they can transact together by doing frequency sharing. Similarly, 1086 tone RU can be allocated to 106 tone RUs can be allocated in a 20 megahertz band by an access point. And then entire 20 megahertz band is also available to be allocated to a particular user. So if a user has a higher bandwidth requirement, it can be allocated a 20 megahertz tone. So what we understand here is, say, if the AP has a 20 megahertz band available, this is the way it can allocate bandwidth. It can slice the bandwidth for different users. Now it is also possible that an AP, what it can do is, a particular user has a higher throughput requirement. However, other user has a lower throughput requirement. Then what it can do is it can allocate a 106 tone band or an RU to one user and a lower band of 52 tone RU to another user. And since the third user has, or third or fourth user have a even lower throughput requirement, then what it can do is it can allocate this 26 tone and this 26 tone RU to the third or the fourth user. So AP has the flexibility now to choose how much band or how many tones it wants to allocate to a particular user, and it can slice the band as per the user throughput requirement. So it can choose this 106 tone RU for the highest throughput requirement user, followed by this 52 tone RU, and followed by the 26 tone RUs. And that, thus it can allocate the entire 20 megahertz band and transact with four users as per their quality of service requirement. So this is for 20 megahertz. Similarly, we have RU allocation for 40 megahertz also. So if an AP has access to 40 megahertz band, if a 40 megahertz band is available for transactions, then we have such kind of a 26 tone RU allocation that is possible on the 40 megahertz band. Again, there is a guard interval to avoid any leakage of signal in any other nearby transactions that are happening. We have null subcarriers being placed to avoid leakage of signal that is being transacted from one user to one user and to the other user. And what we now see is now there is an RU allocation possible of 220 megahertz also in 40 megahertz band. So one particular user can be given 120 megahertz band out of it, and other user can be given another 20 megahertz band out of it. So say there are two users present and an AP has access to to this 40 megahertz channel. What it can do is it can divide the band into 220 megahertz band and connect with the two users together in frequency domain, and share the band with those two users and remain connected with those two users together. Just to re-emphasize, this was not possible before, because if say a 40 megahertz AP was, if say an AP which has acquired a 40 megahertz channel wanted to connect to two users before, what it had to do was to do time sharing. It was to first say do a transaction of 140 megahertz with one particular user and then move to second user and do a transaction of another 40 megahertz. However, now what is possible is both the users can get connected on a 20 megahertz band, do frequency sharing among themselves. However, in time, they can remain connected to AP, and thus it helps in better managing the latency at the receiver's end. There are less number of jitters and less number of say packet drop that happen because of such kind of such kind of frequency allocation, OFDMA frequency allocation. And say if only there is only a single user, AP is free to give that entire 40 megahertz band to one particular user. So the philosophy remains the same for 80 megahertz also. So this is 80 megahertz OFDMA allocation, the flexibility that that the AP has in allocating bandwidth to the user. And I won't go over it in detail, but the philosophy remains the same. Say if an AP wants to get connected with three devices, first device has highest throughput requirement, followed by second, and followed by third and fourth device. What it will do is it will allocate this 40 megahertz band to the first user, followed by this 20 megahertz band to the second user, and for the third and the fourth user, it can allocate these two bands. So if there are more users with lower throughput requirement, what it can do is it can take these slices of bands and allocate to other users, and these slices of bands and allocate to other users also who that has lower throughput requirement. So more users can also get connected to the AP by doing frequency sharing and continue to remain connected with the AP.
Similarly is the philosophy for 160 megahertz. So I won't be going over in detail on this, but it just is a duplication of 80 megahertz to 160 megahertz. Okay, now we come to the extended range packet format that got introduced in 11 AX, which is Wi-Fi 6, and how the new packet format has helped in improving the range of the transaction. So there are three things that 11AX technology has introduced, Wi-Fi 6 technology has introduced in this packet format. One is the preamble boosting. So in every packet format that we would see, what we would see is there is a preamble, which is then followed by data. This is the way a packet gets constructed from the PHY perspective. So there is a PHY preamble first, and then there is a data followed by a data. For extended range, what we need to understand is we need to understand that both preamble can be received at a longer range as well as data can be received on the longer range. For data to be received on a longer range, a new coding scheme, which is dual coded modulation, got introduced. What it does is in the frequency band in which we are transacting, the same data in the frequency domain gets replicated. So whatever information we are sending here in frequency is getting replicated here in frequency. So a receiver, when it receives the data, it receives multiple copies, say 2 copies of this information, and it can do some kind of a combining at the receiver, does some kind of combining to help it receive the data in low SNR regimes also. So by low SNR regime, we want to emphasize that we are transacting at a longer range, hence the SNR is low. So for low, in longer range, when the SNR becomes low, when the receive power is low, the receiver can combine this information and decode the data in low SNR regime. So DCM is the modulation that got introduced to decode the data. For preamble to be received in low SNR regime, what got introduced is this part of the preamble got boosted by 3 dB, and this part of the preamble also got boosted by 3 dB. So this helps in improving the SNR of those parts of the preamble by 3 dB in longer range scenario. For the other portions of the preamble, there was a time duplication that was present for other symbols of the preamble. Hence, what the receiver will do is it will look into both of these symbols, combine them, and then decode it, and hence improve its decoding efficiency. And it is now able to decode in lower SNR regions because there is a time domain duplication. So three things we have here. One is power boosting, which is for few symbols of the preamble. The second is time domain duplication of the same symbols in the preamble. Here and here we have time domain duplication. The receiver needs to combine the duplicated information that it is receiving in time. And then on data, we have duplicated information in frequency that the receiver needs to combine. And when it does some such kind of combining of information, it can decode the data in lower SNR regime as well as in extended range. When the range is large, when say AP is far off from the station, and the SNR that the station sees is low. In such kind of scenarios, such kind of a packet format helps. The third thing that is introduced is a longer GI of 3.2 microseconds. So in the previous technology, we saw that the guard interval was up to 0.4 or zero point 0.8 microseconds. Now a guard interval, as we discussed, helps in avoiding inter-symbol interference in OFDM. If say we are in a longer range scenario, we will experience channels which has a higher delay spread. Okay, and to be able to transact in channels that have higher delay spread and to avoid inter-symbol interference, we need to have a higher guard interval also. Hence, in Wi-Fi 6, this guard interval of 3.2 microsecond got introduced that we have here, which enables that in longer out range and outdoor applications, when there are multipath components, different multipath components coming in from different reflections in a longer range scenario, the delay spread of the channel that we observe is high, and we need to construct or have a longer guard interval here so that there is no inter-symbol interference in those cases and there is a smooth transaction that can be enabled. So these are the few features from the PHY perspective that enable longer range transaction in Wi-Fi 6. Okay. So now we move on to the downlink OFDMA and the MU transaction that got introduced. So downlink OFDMA, downlink MU was present in VHT or Wi-Fi 4 also, sorry, or Wi-Fi 5 also, but Wi-Fi 6 introduced downlink OFDMA and MU transaction together with uplink 1. And how this is enabled is first, so the basic frame exchange is how this is done is first, say AP gains a channel access. So it does some kind of a channel sensing and finds out whether the channel is free or not. So this axis, the y-axis, has to be considered as a frequency axis. Okay, so this is a frequency axis. Now what it does is, say it has acquired this particular band of channel. What it will do is, in case of OFDMA, it will slice the band among different users and transact. Say an AP has to send information to multiple users together. So it will slice this band among multiple users, and in the same packet itself, it will send the data to multiple users together. Again, it will send some kind of a trigger to the user, letting them know that they need to send an ACK back. So after 16 microseconds, an uplink OFDMA transaction will be enabled by all the users, in which all the users will send an ACK or a block ACK back to the access point, letting the AP know that they have received the data or not. And this they can send in the same band that was allocated to them. So this is the way an downlink OFDMA transaction gets enabled. So when an AP wants to send data to multiple users, it first accesses the channel, then sends the data to multiple users among different bands that it allocates to different users, and then requests the users to send back all the ACK together. Note that this was not possible before because uplink transactions were not possible before in Wi-Fi 5 technology. So to even to get an ACK back, the AP would first pull the first user. Then after 16 microseconds of receiving the ACK from the first user, it would port the second user, then the third user and the fourth user. Now what it can do is it can get the ACK back from all the users together. So the efficiency of the previous technology was very low when multiple users were getting connected. This all improved by having this kind of an OFDMA or a multi-user MIMO technology in Wi-Fi 6. This is the case we consider where we have downlink transaction where AP wants to communicate to multiple, when AP wants to send data to multiple users together. Say the what we have a scenario is another way around where multiple users want to send data back to AP. Okay, so in that case, what an AP does is AP first access the channel by doing some kind of a carrier sensing. It first access the channel. After having accessed the channel, say a particular frequency band, it sends a trigger frame to all the users. In this trigger frame, it tells the users what part of band is allocated to each user. So each user understands that, okay, this part of band is allocated to first user, this part of the band to second, this part of the band to third. And then after 16 microseconds, all the users send back the data, whatever data they want to send to AP in uplink OFDMA PPDU format or in uplink OFDMA frame format to the AP. Then what the AP does is after receiving data from each user in their respective frequency band, it decodes them and finds out whether they have been received correctly or not, if and sends an ACK back. So after 16 microseconds, an AP will send an ACK back, ACK packet back, which will have ACK for each of the users. So each of the user will understand simultaneously whether its data was received by the AP correctly or not. So because all these transactions of uplink and downlink can be done in frequency sharing, there is no time sharing involved. We need not, the ACK need not be sent to each user separately. They can be sent by to each user in single packet itself. Together with, if the user needs to send an ACK back for say the downlink packet that it is receiving, all the users can send it together itself. This has helped in improving the efficiency of the entire protocol when multiple devices get connected to the access point. Hence, in dense environment, such kind of OFDMA as well as MU technology uplink as well as downlink has significantly improved the performance and the system level throughput when multiple devices get connected. So yeah, so this is probably the last slide I have here. And
Ankit, one doubt. Is there any limitation while allocating the frequency? So that frequency will be subdivided into multiple channels, right? So for each channel frequency, is there any limitation? for user allocation in terms of user allocation?
So it depends on the band. So if they say the band is, if the user is able, say if the user is able to accept a 40 megahertz packet, let us take this case that we have an 80 megahertz band that is available. If the user is can accept a 40 megahertz packet, then or an 80 megahertz packet, then as per the system requirement, if there is no other user present, then the AP can allocate the entire 40 or 80 megahertz to that particular user. So did I answer your question?
Yeah, in terms of let's say for example in say stadiums and there will be a more users, right? So for that particular scenarios, how it will be divided? Is there any limitation for each channel? So this many number of subdivisions can be done. So likewise for each frequencies. So for example, in 5 gigahertz, we have some number of channels, right? So for each channel, is there any limitation for
Yeah.
the so this many users I can allocate?
Yeah, so say in a 20, we have limitations. For example, in a 20 megahertz channel, I can allocate up to 17 users, not more than that. So that is the kind of limitation that the standard imposes. So say I can allocate up to 17 users in 20 megahertz.
Okay.
Yeah. So there are specific restrictions in the standard on how many number of users it can have in a particular band that can be transacted together. So in 20 megahertz, the standard has given the flexibility to have up to 17 users.
Okay.
And say when there are multiple devices, say in kind of a stadium scenario in a dense environment that are getting connected, it is AP that decides on how much bandwidth it wants to allocate to each user. So depending, say, on the kind of throughput requirement that a user wants, AP will have some kind of an algorithm or some kind of a scheme by which it will decide on what bandwidth needs to be allocated to each user. So it is implementation specific. There is nothing defined in the standard. It is something that is free, and AP is free to allocate as per whatever is the implementation at AP's end.
Okay. So one more question is how AP identifies the user's data requirement,
So
data
there
rate
are some
requirement?
specific trigger frames that have been introduced in the standard. So there is a buffer status report data frame, for example. So those kind of trigger frames, AP will first send to multiple users, or it will poll multiple users together, find out what kind of buffer status is present with multiple users, and it will understand what kind of bandwidth needs to be allocated to multiple users. So yeah, there are specific higher layer packet formats, trigger frames, say MAC layer trigger frames are there, which help in identifying the kind of throughput that is required at user's end.
Yeah. Okay.
Mm,
Thank you.
sure.
Uh, Hey Ankit, I have a question here on the maximum number of users that are supported in 20 megahertz. So right now it is 17 if we go in the previous slide. So if I allocate 26 to an RU, the smallest one in 20 megahertz, the maximum 9 number of users, or I believe 8 number of users at same time can be accommodate. Then wanted to understand like how we come to a number 17.
Yeah, so that is right. So if you were to understand the question is, say if I have this 20 megahertz band available, I do the slices in the lowest frequency slice that is available to me, and then what I do is I can have at most 9 slices of 26 tone RU, and thus I can only support 9 users. So how do we get 17 users? So
Yeah,
what we also need, yeah, so what we also need to understand is we can also spatially multiplex users. So we have multi-user MIMO also. So say in this 106 tone or a 52 tone RU, we can have multiple users spatially multiplexed also. So we can have 4 streams that are sent to 4 users in this 52 tone RU, which are spatially multiplexed. Each stream is for a one particular user. So we can have 4 users, say, communicating in 52 tone, and we are doing spatial multiplexing also. So one is frequency division of the band, and one is spatial multiplexing. This we can divide the space also and spatially multiplex users also in the same frequency band. So if we were to find the maximum by understanding the spatial multiplexing together with frequency division, then the number that comes up is 17 users.
Okay, sure. Yeah. Thank you.
Hmm. Okay, so we are open for questions here. Just people can feel free to chime in. Students who are connected, other engineers, just feel free to chime in.
So Ankit, one more question. Do we have any pictorial representation where both is done, like spatial multiplexing of the users as well as the frequency-based division of the user?
I
Any
don't have it right now. Yeah, maybe I can send it to you separately.
sure,
I don't have it right now. Yeah, yeah,
sure. Okay, sure.
yeah,
Thanks.
sure.
Ankit, what will be the PAPR for the OFDM and OFDMA packet? So for a higher bandwidth range, typically, any idea on that?
So yeah, if I understand correctly, it remains more or less the same. I can check, but I think the PAPR requirement for OFDMA, there are some symbols in the packet format that may require, but in general, it remains more or less the same. The PAPR requirement doesn't change in OFDMA frame format.
Okay, so how much the number actually? Any idea on the
So it
number?
is around, yeah, 10 to 12, yeah, means the mean is around 10 to 12 dB. So PAPR is a very subjective topic in the sense what kind of data gets transmitted in a particular symbol. So so depending on what data is in a particular symbol, if say the data has a lot of duplication, the PAPR would be very high. Say if the data is duplicated in frequency domain, a lot of common things are there in frequency domain, the PAPR would be very high. But say the data is not, if there is a very a different kind of data that is getting transmitted across frequencies, then the PAPR will be low. In general, it is around, say the mean is around, or the 70 to 90 percentile point is around 12 dB or so. That is what the benchmark is, say, for the PAPR of OFDM symbol.
Yeah. Okay. Thank you.
Yeah.
Ankit, one more question on the same lines that wanted to understand if there are any requirements on frequency accuracy when we are operating with multiple user in OFDMA scenario, like carrier frequency offset requirements. Are there any which standard specifies?
Yeah, so that's a good point actually. So if we come and if we try to understand, so what happens is, say in frequency domain, previously the tone spreading, sorry, the tone gap between the two tones was 312.5 kilohertz in the previous standards. It was not lower than this. It got lower only for Hue standard. This is because when the technology evolved and when the crystals became more accurate, the technology then was able to support a delta F of 78.125 kilohertz. So say if the crystal ppm was high, which was the case, say maybe 15 years back or so, the crystal ppm was high. In that case, the CFO at the receiver would have been high. So if the CFO at the receiver is high, and if the tones are very close by, what happens is there is a lot of inter-carrier interference that is possible. But now, because the technology has evolved and the CFO, the crystals have been more accurate, and the crystals, the CFO that is seen at the receiver's end is low, it is possible to have a lower tone spacing of 78.125 kilohertz here. So in general, the CFO tolerance for hue is lower. However, the technology has evolved to that level that whatever CFO is present now is quite low, and we are able to have good transactions with the hue technology, with hue frame formats.
Uh, Okay, thanks. One more question in the same line, if multiple in OFDMA scenario, when multiple users are operating in the same bandwidth, at that time, are there any constraints on CFO or particularly?
So when multiple users are operating together,
Yeah.
so there is one thing which we need to point out. Say when specifically, let us take the case of uplink transaction. So when say all the users are transacting together to the AP. Okay, in this case, what we need to ensure is the CFO that the AP sees from all the users. Say in OFDMA, there are multiple users who are transacting an uplink packet to the AP. So in that case, we have a very stringent requirement that the CFO between the access point and all the stations should be within 300 hertz. So that kind of a requirement we do have in case of uplink OFDMA transactions.
Okay, sure. Thank you.
Yeah. Okay. Yeah, maybe we can just wait for a minute more. So yeah, I encourage all students also, if you have any questions, to come forward. Okay, I think then we don't have any further questions here. So yeah, if people are interested to get more details about the PHY layer, they can refer to this standard 802.11x draft 8.0 Wi-Fi 6. It is a quite detailed standard where people will be able to find much more information, not only from PHY perspective, but from Mac perspective or from higher layer perspective also. And for students who are interested, say in physical layer design, say for Wi-Fi, Bluetooth, etc., that NXP is into, what I would suggest is, if you want to pursue a career in this domain, then the courses that you do specifically on signal processing, on wireless detection, wireless communication, MIMO technology, those are the courses that are eagerly sought after. Those are the skill sets that are eagerly looked into. How familiar are you with MATLAB? How familiar are you with the signal processing toolboxes in MATLAB, C++ environment? So yeah, if a student wants to pursue a career in this field, if the student finds this kind of physical layer design field interesting, yeah, it is highly theoretical. One needs to be good in theory. So all the courses that say someone in telecommunication specialization or communication and signal processing specialization does, one needs to be very good at it. Information theory, I would say, detection and estimation theory, etc., etc. So yeah, but yeah, we are here to welcome all the great talent, and anywhere else also, if you find interesting physical layer work, I would encourage students to just go over these topics in more seriously and in more detail. Yeah. Okay. Thank you, everyone. Then maybe we can stop here. Thanks a lot for your time, and it was a pleasure to be able to present this to everyone here. Thank you.
Thank you, sir. Thank you so much. It was a very insightful session. Hope everyone has that grab a lot of knowledge from you. Thank you.
Thank you.
Thank you.